in an email, a big lengthy email to the class that kind of has the outline for the week. So I sent that late last night. I'm so sorry. Molly is going to set up a group meet. If you want to include numbers here in the chat, if you don't want to publicly put your number out there, I'm pretty sure there's a way that Molly or whoever sets it up I can email a link to join. Okay, so if you don't feel comfortable putting your number in, just wait for that link. Once you get it set up, Molly, if you will email me the link to join in case someone's not here present on this lecture this morning or doesn't get the info, I will also email out the joining info and you can just join that way. That's at least how we did it last fall. Okay. Otherwise, it seems like most everybody's throwing their numbers there, but that's a lot of work, Molly, for you to put all those numbers in. So everyone give a round of applause to Molly for being willing to do that for everybody. It's very kind of her. So other than that, if there's any questions from you guys right now, any just general questions, I know I've got some emails I've got to respond to. So if you sent me an email this weekend and I have not gotten back to you, or if you sent me one yesterday and I have not gotten back to you yet, I have an office hour right after this lecture and that'll be my first goal is to respond to any unanswered emails. So if you've already sent me your question, just hang tight. But if there's any other questions pressing, type it in the chat. You can unmute yourself. If not, then we're going to continue with where we left off on our measurement slides. So grab your measurement slides, grab your calculator. If you need some extra paper, we're going to be doing a lot of working problems today. And the purpose of this is to get you comfortable with the style of questions that I ask on the exams. Also the quiz. Here's another announcement. You have your first quiz today. It's 5 questions. Somebody make sure you're muted. I'm kind of getting some background noise. Your first quiz is today, and so you'll have 20 minutes to complete it. It's on material from last week, either one of those lectures that we had. So don't forget to get on at some point today and take that quiz. All right. Okay, well, I'm going to share my screen. Hold on just a second. I saw there's a question in the chat. Okay. Let me pull the chat back up. Bailey said, how many points are quizzes worth again? 5 points. So it's 5 multiple choice questions, but don't take that lightly. Sorry, I'm getting some really interesting light behind me. Don't take those quizzes lightly. And here's why. Let me put it to you this way. You have 10 quizzes over the course of the semester. That adds up to half an exam's worth of points. So that is kind of a big deal when you consider them all together. But all right, well, hopefully you can see my screen. I'm going to turn it sideways because I feel like you just get more room to work things this way. We are going to review for just a second. So let me reorient you. This is kind of where we ended last week. We worked some of these problems. Remember, we talked about prefixes and we talked about, what else did we go over? Prefixes. We talked about base units like the meter, the liter, and the gram, and having kind of a tangible feel for how big a meter is, how much a gram is when it comes to mass and things like that. And then we started putting things together and working a few 1-step, 2-step conversion problems. So we're going to do a few more of those. And then I have this slide right down here that I meant to get to last week, but we didn't quite get here. So we'll fill this in because this is kind of a recap of the first half of the lecture, and then we'll jump into the second half. So let's look at this problem right here. This is a conversion problem. We're going to use a conversion factor. We're just going to convert between units here, if you remember what that is. And it's just kind of in a word problem style. So I like this problem because it's starting to orient you to a word problem. So let me turn my pencil. Here's what the problem says. You must transfer 0.000067 liters. So that's a really small amount of a morphine solution. So we're nurses today. Okay. We're transferring morphine solution into a plastic tube. How many microliters is this? Okay. So this number makes my head hurt when I look at it because all the zeros. So we're going to convert it to microliters so that we can better read it a little more easier. So if we're going to convert from liters to microliters, there's our 2 units right there. We need a relationship. Does anybody remember how many microliters? Which one's bigger, by the way, a liter or a microliter?
Liter is bigger.
Liter is bigger, okay? So how many microliters are in a liter? That's the relationship we need to know. In 1 liter, how many microliters are present? Anybody remember? You could write it scientific notation or standard number.
It's a million.
It's 1,000,000. I don't know who said that, but good job. There we go. I'm going to write scientific notation. 10 to the power of 6, that's 1,000,000, okay? So we're going to start with the number that we're given in liters, and we're going to convert to microliters. We want to cancel out units. Remember that part of a conversion factor problem. You got to cancel the unit that you don't want. So 0.00, how many zeros is that? 1, 2, 3, 4, 6, 7 liters. And we're going to multiply by our conversion factor. Sometimes people like to write this initial number over 1 just to show themselves, hey, this is on top. You don't have to do that, but this liters is on top. And so now we're going to plug in our relationship as a conversion factor. I'm going to put liters on bottom because I want that to cancel. 10 to the 6th microliters on top. Now I'm going to show you how liters cancel because we have 1 on top, 1 on bottom when it comes to the units. Now we're actually going to do the math. So once you set it up properly, that's just half the battle. Now we're going to do the math. 0.000067 times 10 to the power of 6. Okay, I'm ignoring this 1 down here. Again, you don't even have to write it because dividing something by 1 numerically never changes your answer. Okay, anybody get an answer there? How many microliters is that?
67.
67 microliters. Okay, that's a much more manageable number for our brains to handle. Did somebody ask a question?
No, I was just going to say, you just move the decimal places that many times. You don't have to multiply it all out. You can just
you can plug in your calculator like this, or you can know that you take your decimal because it's 10 to the power of 6. We're going to move the decimal 6 places to the right. Okay, if that just helps you. If it was multiplying by 10 to the power of 3, you'd move it 3 places to the right, so on and so forth. Thank you, Kristen. Okay, another word problem. Let's look at this. I'm going to need y'all's help. I'm going to need somebody to glance up at those tables from earlier that has all our equivalent relationships. Any marathon runners in class with us? We're honored you're here. We're not like you. You're different. Okay. Any marathon runners? No? Yes? You don't have to be shy. So 26.2 miles is the distance of a marathon. So my husband actually ran his first marathon last year. This was right before COVID shut everything down. The Little Rock Marathon happened like first weekend of March. And then literally the next weekend, everything was like shut down. So he was proud to get it in. But 26.2 miles, that's the distance of a marathon. How many kilometers are in a marathon? Okay, so we're going to convert. What's our units here? We need to identify. It's miles and kilometers. So we need a relationship. We need to know, kind of like a dozen is 12 items, how many kilometers are in a mile, or vice versa, how many miles are in a kilometer. Okay, I see in the chat, Rachel said 1.6. Is that how many? I'm pretty sure that's how many kilometers are in a mile. Is that units on there? You just threw a number on there. So we want to know how many miles equals how many kilometers. Yeah, okay, so she said 1.6 kilometers are in 1 mile, which makes sense because I do know that miles are bigger. Anybody ever been over to Europe? And when you run a marathon over there, they're like, it's 45 kilometers. They have those stickers on the back of their cars, not the mile stickers. So miles are bigger, okay? All right, so we're gonna take 26.2 miles. And we're going to now multiply by this conversion factor. So for every 1 mile, we actually run 1.6 kilometers just because the unit there is, the kilometer is smaller. Okay, so now you cancel out miles because you have it on top and on bottom. And then you do 26.2 times 1.6. So is it around 45? Was I right or was I way off?
42.
42? Is there a decimal with that? 42 exactly. 42, 41.92, 41. Okay. So if you round, it's 42, but 41.92 kilometers. Okay. If you notice, if anybody has checked out that dry lab on Blackboard, by the way, in places where I need to get you to give me a specific number of decimals, just because Blackboard, I just have to give a lot of directions on how to type your answers in because of Blackboard. I will tell you how many decimals I want. So pay attention. Just make sure you read instructions very thoroughly when you do these online assignments, because it'll tell you put it into 2 decimal places or 1 decimal place or whatever. Okay. All right. Last one before we kind of jump into something else. How many milliliters are in 2.54 gallons? Okay. So here, gallons is not a unit with a prefix, but it is just a different unit. Okay. So we need a relationship that relates milliliters to gallons. Obviously, gallon is way bigger. So there's going to be a lot of milliliters in a gallon. So for every 1 gallon, I'm wondering how many milliliters is this? Now, if you go look at that volume table, I don't know, do we have a relationship that directly relates milliliters and gallons? We might have to go gallons to liters. We might have to relate those and then liters to milliliters. So instead of saying how many, why don't we actually, okay, Bailey says 264.2 gallons is in 1,000 liters. Okay, we can use that. That's totally doable as long as we have a relationship between the two. So 264.2 gallons is in 1,000 liters. Okay. So then we also know, she said 1,000 milliliters is in 1 liter. That's correct. So we're going to start with this amount of gallons, and we're going to convert 2 liters, cancel gallons, then we're going to convert from liters ultimately to milliliters. Okay. So go ahead and start writing that out. Oops. 1 liter on the bottom, 1,000 milliliters on top here. Okay, so your problem should look something like this. Here's what I love about iPads. You can like adjust it. It makes students so mad when I like rearrange my notes to make them more organized, and you can't do that on paper. Okay, gallons will cancel, liters will cancel. Now we have to do all the math here. I mean, that last 1 at the bottom, we don't have to divide by that, but you got to do 2.54. Here you have to do times 1,000, and you have to then divide that by 264.2. Okay. So in your calculator, you do 2.54 times 1,000, divide that by 264.2. Then you're going to multiply, we have another 1,000, multiply by 1,000 again. Anybody have the final answer yet? How many milliliters is this? Should be a pretty big number. Fairly big, I should say. Glenn says 9,613.9 milliliters. Is that what y'all got? Or yes, you can write this in scientific notation. If we put it in scientific notation, we make it a number between 1 and 10, right? So you move the decimal 3 places to the left. When you move decimal left, exponent increases. So it'd be 9.6. You could round if you want, times 10 to the 3 milliliters. Either way. Questions on that? Okay, so that's simple conversions. You'll probably have some stuff like this on your first exam, but this is not, I consider this to be level 1 stuff, okay? So we're gonna go to level 2 in just a minute. All right, let's kind of recap what we've learned so far. We talked about units a whole lot last week, and we said numbers without units are meaningless, okay? So please always include, do I put out study guides for exams? You know what? Last semester I did put out study guides. In the past, I would have argued, you're making your study guide right now. But I have done those in the past. And if basically it's a summary, it's kind of like hitting the high points of the chapter. And I put a few practice problems perhaps, but not a ton because we do so many practice problems in lecture, okay? All right, number 2, how to write and manipulate numbers in scientific notation. That's what we learned. Okay, so how to multiply, divide, add, subtract. And then we learned about prefixes. Okay, what were the 4 that I said you should probably take the time to memorize so that the exams are less stressful for you? Anybody remember the 4 I encourage you to memorize?
Centi, milli, micro, and nano.
Not nano. We started with kilo was one,
yeah.
and then centi, milli, and micro. Okay, and their relationship to the base unit. Okay, so how many of each of these things are in a base unit, or how many base units are in each of these things? Either way, you need to memorize it. Whatever is easiest for you. Okay. All right, so now we're going to move on. We're going to look at some other properties. So remember, just big picture here, what we've talked about so far is chemistry is the study of matter. We look at properties of matter, like the length or the mass or the volume of matter. And now we can also measure things like temperature and density and specific heat. Okay, these are other useful properties. So let's talk about temperature first. So this figure is really nice because temperature, you realize, is more complex than we think sometimes. We've got 3 different scales for temperature, and you see all 3 here. We got the Fahrenheit scale, Celsius, and anybody heard of the Kelvin scale before? This one is used a lot more in like research. Fahrenheit and Celsius are used more often in medicine and things like that, but we do have the Kelvin scale. And on each of these, it points out different temperatures we might relate to. So boiling water, that's the top temperature you see marked off on all of these thermometers. Body temperature, room temperature, where water freezes, okay? And so I want to point out a couple of things because the first thing I want to point out is where water freezes on each of these. So I'm gonna kind of box this in. So here's where water freezes. So for Fahrenheit, freezes at 32. Celsius 0, and Kelvin is kind of crazy random, 273.15. And that 0.15 is important. When you're writing these or converting between these, don't ever forget that 0.15. Now I want to point out where water boils on each of these. So for Fahrenheit, it boils at 212. Celsius, it boils at 100. And Kelvin, 373.15. So the first thing you may notice is that Kelvin and Celsius, when you look at the difference, okay, between these values for both Celsius and Kelvin, what do you maybe notice? Where water freezes and where water boils. The difference between those temperatures.
100.
They're both 100. Thank you. Okay, it's a difference of 100. So what that means is that an increase in 1 Celsius is equivalent to or equal to the increase in a Kelvin. So the units are the same size. If you go up in 1 Celsius, you go up in 1 Kelvin, vice versa. Okay, so the units here, same size. In other words, 1 Celsius equals the size of 1 Kelvin. But it's different for Fahrenheit. What is the difference between 212 and 32? What is the difference in the freezing and the boiling point of water on the Fahrenheit scale? Ashlyn said 180. Okay. So which unit is bigger, a Fahrenheit or a Celsius? Anybody? You have to travel 180 degrees in Fahrenheit to get to the same point on the Celsius scale that you only have to travel 100 units on the Celsius scale to move. So yes, Zoe says that Celsius units are bigger. Yes, Celsius units are bigger. Fahrenheit units are smaller because you have to travel more of them to get to an equivalent boiling point of water, for example, equivalent kind of temperature mark. So this was a difference of 100 and 100 and 180 on Fahrenheit. So because we have these 3 different scales, we're about to learn how to convert between these units. So Bailey says, why do we have such different scales? Is there a reason? Honestly, that's a great question, Bailey. I don't know why we have different It's kind of like we have different languages, right? We have just people have different approaches to how they're going to measure things and do things naturally. So these 3 have just evolved over time, but I don't know why that they are all so different. Okay, so one other thing I want to point out before we jump into how to convert these things. By the way, these complex equations down here, I will give you on the exams, but these up here, I want you to know how to do. And they're very simple. The ones I'm gonna ask you to memorize or know are very simple. So Celsius and Fahrenheit, if you look at the units in parentheses there, notice that we put the little degree symbol with Celsius and Fahrenheit. We don't with Kelvin, okay? So it's actually incorrect to say a degree Kelvin. That's not a thing. It's just a Kelvin, okay? But you should say a degree Celsius or a degree Fahrenheit, all right? All right, so if we want to convert from Celsius to Kelvin, okay? So if I give you a temperature in Celsius and I say, what is the equivalent temperature in Kelvin? Well, remember that the units are the same. It's just that the starting places are different. If you go back up here and look at 0 on the Celsius scale is 273.15. So that's a very easy way to make these conversions. Anytime you have a Celsius temperature, so you'll plug in your degree Celsius temperature and all you do is add 273.15 and that gives you the Kelvin temperature. You can prove it to yourself real quick if you plug in 0 for Celsius, 273.15 Kelvin. Okay, vice versa. If you have a Kelvin temperature and you need to convert back to Celsius, you just plug in the Kelvin temperature and you subtract 273.15. So the reason I say just go ahead and memorize these is because they're fairly simple. Okay, conversions between Fahrenheit and Celsius are way less easy. They're a little more complex. But you'll always have these equations available to you. I provide a resources page for exams. It's kind of just a page where I put a really good periodic table for you and then any, I think, essential equations that I don't want you to take the time to memorize, I put on that resources page. So you just have quick access. It'll be on Blackboard. So these equations will be on your resources page for exam 1. Notice that we do not have a direct way to convert directly from Fahrenheit to Kelvin. Okay, we always have to, Celsius is always the middleman. So if you're asked, like, here's a Kelvin temperature, what's the Fahrenheit? First, you have to convert to Celsius, okay? And then vice versa. So let's look at this first one. This first one's if we want to get a temperature in Fahrenheit. So let's say we have the temperature in Celsius and we want to know what is the equivalent in Fahrenheit. Here's the equation you use. This place right here is where you're going to plug in your Celsius, degree Celsius temp. All right. The reason I'm pointing this out is because there's all kinds of letters in this equation, right? And you might think, sometimes I'll see people plug it in with the arrow and then also right here, and that's not correct. This right here is just the unit for this 5. All right, so you do not plug your temperature in twice. These right here are units. Where the arrow is pointing, this is where you plug your temperature in, okay? But it's important to include units on all your numbers here. So you would plug in your Celsius temperature. You're going to multiply it by this fraction 9/5. Where does that come from? Real quick, I'm going to explain it. If you go back up here to these temperature scales, if you take 180 and 100, we're going to orient them so that the units look, orient them so that the units look like this: Fahrenheit on top, Celsius on bottom. So that would be 180 degrees Fahrenheit over 100 degrees Celsius, right? Because those give you equivalent values on the temperature scales. If you simplify that as far as you can go, you get 9/5. Okay. We take off zeros, you get 18 over 10. If you divide that both by 2, you get 9 over 5. That's where that fraction comes from. We're just relating, it takes 9 degrees move in the Fahrenheit scale is equivalent to a 5-degree move in the Celsius scale. Okay, so you plug in your Celsius temperature, multiply it by 9/5, and then you're going to add 32, and you'll get the temperature in Fahrenheit. All right. Notice there's an order of operations here. Anybody remember the
PEMDAS.
Okay, people have different alliterations for order of operations. I always learned it with "please excuse my dear Aunt Sally."
My dear Aunt Sally. Yeah.
that one. So remember, anytime you have whatever alliteration works for you, but anytime you have parentheses, you have to do that first. Okay, just a reminder, mathematically, you can't just plug this in and do anything you want. You have to multiply it by the fraction first, then add 32. All right, come over here, the equation on the right. This is if we have the temperature in Fahrenheit, we plug it in right here. And we want to calculate the temperature in Celsius. All right, notice the parentheses have moved. Now, the first thing we're going to do is subtract 32. Okay, then we multiply by 5/9. We have a reciprocal here. Okay, so that's why I'm giving you these, because the two places people screw this up is they'll either do the order of operations wrong or they'll get the reciprocal of the fraction incorrect. So when you're converting from Fahrenheit to Celsius, it's 5/9. Why do we do that? Because if you notice, when you do the addition or subtraction problem over here, you have degree Fahrenheit, and then that will cancel with your degree Fahrenheit, and you'll be left with degree Celsius. That doesn't cancel. And you want the temperature in degree Celsius. So anyways, let's now work a problem. Let's do a practice. Okay, here's the problem. Body temperature is 98.6 degrees Fahrenheit, roughly. I know everybody's body temperature is slightly different. What is body temperature in Celsius, and what is body temperature in Kelvin? Okay, so use these equations up here. First, we're going to convert from Fahrenheit to Celsius. So which equation do we need? We already have the Fahrenheit temperature. We want to convert to Celsius. So we need the equation on the right or the left. Which one?
The Fahrenheit or Celsius one on the right.
Yes, Blake, we need this one over here. So we're going to plug in, it says degrees Celsius equals 5 degrees Celsius over 9 degrees Fahrenheit. So 5 degrees Celsius over 9 degrees Fahrenheit. And then we put our, we're going to multiply that by, we put our parentheses. Now this is where you plug in your Fahrenheit temperature, 98.6 degrees Fahrenheit. And you're going to subtract off 32 degrees Fahrenheit. So you'll do 98.6 minus 32 first, get that value, then multiply it by 5/9.
37.
37 degrees Celsius. And actually that might be common knowledge for some people, especially if you're kind of in further into the health science world, maybe you already have a job there. 37 degrees Celsius is body temperature. Okay, now we want to know what is it in Kelvin. So we're going to take this temperature in Celsius. How do we convert to Kelvin?
Add 273.15.
Yes, 73. Don't forget the 0.15 or you won't get full points. Okay, so that should be 310.15. Is that what you got? Kelvin?
Yes.
Okay. So that's it. Those are temperature conversions. Questions on those? What questions do you guys have? Okay. All right, well, we're going to move on then if there's no questions. So you'll definitely, I usually always throw a temperature problem on exam 1, okay? We're also going to talk about energy. Really, the end goal here is to get to specific heat. This may be a new term for you, and that's okay. We're going to walk through it slowly. But we're going to start with our discussion on energy, which I think is very appropriate following temperature because a change in energy, a release or an absorption of energy is usually accompanied by an increase or decrease in heat, okay? Right now, if you feel like right here at the back of your neck, you probably feel warm slightly because your body's exerting energy to maintain body heat, okay? And so it's releasing energy to keep you at a certain body temperature. So energy is the ability to do work or supply heat. Energy comes in many forms, and heat is just one of the main forms. Okay, unfortunately, like many things in chemistry, property of energy has multiple units, okay? Just the way temperature had multiple units, energy has multiple units. The joule is the SI unit. Okay, remember we talked about there's a system of international units. That's the joule. So you'll read joule if you read research papers or articles or journals. You'll see the units of joules more. Calorie is more often used in medicine. Okay, so calorie is another unit of energy. When you read nutrition labels, right, we read calories. That's actually a capital C calorie. So there's a difference between a lowercase c calorie and then a capital C calorie. And we actually have that difference right over here. Okay, one lowercase c calorie, a kcal is a capital C calorie. So there's 1,000 lowercase c calories in a kilocalorie, which is in nutrition world, dietitian world, you just call that a capital C calorie. All right. But what is the relationship between joules and calories? So 1 calorie is 4.184 joules. So which one's bigger, a calorie or a joule? A calorie is bigger. It takes over 4 joules to equal 1 calorie. So a calorie is bigger. All right, these relationships over here should not be confusing to you. They're just indicating simple units with prefixes, okay? 1 joule, or sorry, 1,000 joules is 1 kilojoule, and 1 kilocalorie is 4.184 kilojoules, okay? We just plugged in K for both. So if this relationship right here stands, then this one also is the same. It's just kilos plugged in on both sides. All right, I'm gonna erase a little bit of my scribbling so y'all can see clearly. All right, now let's define specific heat. So now that you have a little bit of an understanding about energy, what is specific heat? Specific heat is the amount of energy and in the form of heat or heat required to raise the temperature of 1 gram of any substance by 1 degree Celsius. So this is kind of a confusing definition. We're going to walk through it piece by piece. So specific heat is an amount of energy. So when you invest energy into something, for example, if you're going to boil water, you have to turn the stove on or put it in the microwave. You have to somehow add heat to it, which is energy. And it's an amount of energy necessary to raise the temperature of 1 gram of a substance by 1 degree Celsius. Now, remember, is a gram a lot or a little? How much is a gram? Remember that a dollar bill is about the mass of a gram. So 1 gram of a substance, we're not talking about a lot. It's just a little amount. It's just enough to quantify the related specific heat. So because of that, we know we have units for energy are joules and calories right here. So if we're going to write out an equation for specific heat, we plug in the energy term. So we put in either calories or joules. You'll never plug in both. It'll either be calories or joules on top, and you divide that by, in parentheses, I like to put in parentheses, the mass of your substance in grams times the change in temperature of the substance. Okay. Now, why is specific heat important? Why can we appreciate specific heat? Let's look at this table over here in the corner. I'm going to zoom in on it. So we have a bunch of different substances listed, and you're given the specific heat with different units. So this one is the calorie, that first column on the left, and then the column on the right is the same value, just with units of joules, okay? So let's look at this. Ethanol, gold, iron, mercury, sodium, water. Which one of these substances, sorry, I'm reading the chat. You said it was change in heat, not just the heat, correctly? It's the quantity of heat, but we're measuring that quantity of heat by how much the temperature changes of that substance. Okay, so it's just a quantity of heat, just an amount of heat. Okay. I hope that answered your question, Bailey. If you're looking at this table, which one of these substances has the highest specific heat? You can type it or say it. Water, okay? Water down here at the bottom has the highest. So what that means, if we're comparing, let's look at water and ethanol, for example. If we're comparing these two, it's going to take a lot more heat or energy. If you have a pot of water and a pot of ethanol on your stove, it's going to take a lot more energy to heat up the water for it to boil than it would the ethanol. The ethanol would boil first, okay? Now, why can we appreciate this? Let's look at the human body, for example. What percent roughly of our human bodies are water? Quite a good amount, right? Anybody know? Roughly
3/4.
75%, 60, 70, 75%, somewhere in there. So a good amount of our bodies are water, okay? Now let's think about our environmental temperatures, because that's something that changes almost every day. Yesterday, it was like a beautiful 70 degrees in the afternoon almost. Today, it's like 43 degrees, okay? So our environmental temperature changes all the time, and we can't control that. If you live up in Alaska or if you live in Panama, you're experiencing wildly different environmental temperatures. Now, fortunately, our bodies are made of water and not, say, ethanol, okay? Because the temperature of our bodies, they are affected by our environmental temperature, but our body temperature doesn't fluctuate with the weather, right? Thank the Lord, okay? What if our bodies were made of 60% ethanol? What do you think would happen? Because the specific heat of ethanol is way lower, your body temperature would literally fluctuate a whole lot more than if your bodies were made of water. So you can be thankful, you can appreciate the fact that it takes a lot of energy to heat up water or for water to cool down compared to other substances. Let's look at gold and iron, mercury as well. And in fact, all of these four that are in the middle. What do you notice? What could you say about these substances that are in the middle between ethanol and water? They are all metals, okay? So what can we immediately say about metals? Do they have high or low specific heats? Compared to things like water, they have very low specific heat. It takes very little energy to heat up metal. I learned this lesson the hard way. Anybody learn this lesson the hard way? Anybody stuck metal in a microwave? So I grew up my whole life. My mom, she always cooked dinners and stuff. So I learned to I loved cooking and baking, but we had plastic measuring cups, okay? Plastic, safe, childproof, you might even say. For Christmas one year, I thought it'd be really cool to get Joanna Gaines' new metal set of black measuring cups. So I got them. But when you're used to melting butter in a plastic measuring cup your whole life, you forget not to put metal in the microwave. So I'm making cookies. I fill a measuring cup up with butter and I stick it in the microwave for a whole minute. And then I grabbed it and that did not feel good. Okay, so you should not put metal in the microwave. You probably already know this, but allow me to remind you, because the specific heat is very low. All right. Okay, let's do a problem using specific heat. So how many joules? We're going to use this equation, by the way. I'm going to teach you how to use it. How many joules are required to raise the temperature of 132 grams of ethanol by 10 degrees Celsius? Okay, this problem is sometimes where I begin to lose people. So don't let me lose you here. If you have questions, slow me down. I'm going to walk through it very slow. We're going to have to do some algebra, which is something we've not had to do before, okay? You've had algebra, you know algebra. It's probably not your favorite. You're going to have to do some algebra. I want to remind you of a few rules of algebra really quick, okay? If we have A equals B times C, and I want you to solve for B, what do you have to do?
Get B by itself. So
If I want you to solve for B, as in bat, yes, you said it. You have to get B by itself. Okay, if you're
divide by C.
Yes, if you're solving for a particular portion of the equation, you have to isolate that portion. Okay, so here we're going to divide both sides by C. We call that cross division. We're going to cancel C out. All right. So we're going to do some algebra. You're going to see me doing some of these things. Don't be confused by them. It's just algebra. It's just with new terms. Call them A, B, and C if you want. I don't care. We're just using it with the specific heat equation. All right. So keep that in mind. Let's do this problem. It says how many joules? So I'm going to abbreviate this equation. I'm going to call it SH. That's specific heat. I'm going to cancel out calories because we don't want calories here. The question says how many joules. So I'm just going to pick joules. So I'm going to use a J for joules. And then we're going to divide by, I'm going to abbreviate grams as well. G times, and I'm going to put degrees Celsius right there. So here's our abbreviated equation. So it says how many joules. So that's like me saying, hey, I want you to solve for joules. So I want you to go ahead and isolate J. Get J by itself. I'm going to turn my space heater on. So what we just did with the ABC thing, now we're doing it with different letters, but it's still the same principles. So what do we do to get J by itself?
multiplied by grams Celsius.
Yes, we're going to cross multiply, but we're going to cross multiply by two things. And what's nice is you can go ahead and do them both in the same step. That's what I like to do to keep it less steps for everybody. So I'm going to multiply by grams times degrees Celsius on both sides. Okay, if I multiply on one side, I got to multiply on the other side. So now I'm going to cancel out these terms. Remember, if you have it on top and bottom, it cancels. So I'm going to rewrite my new equation. My new equation is this: grams times my change in temperature. This is not just a static temperature. This is going to be the change in temp. Sometimes you may have to go ahead and calculate your change in temperature before you plug it in. All right, here you're already given, it says raise the temperature by 10 degrees. So that is already a change in temperature. But if I said initially your temperature was 35 and now it's 45, you could just calculate that pretty easy. Okay, times the specific heat equals joules. Okay, now we're ready to plug everything in as long as we have everything. So let's find, do we have grams? G is our first letter here. Do we have our grams? Does the problem give that to us? Yes, it does. So go ahead and plug that in. I'm just going to come right over here. 132 grams times change in temperature. We're given that as well. So times 10 degrees Celsius. Don't forget your units. I'm going to shrink this down. Okay. Times the specific heat. Do we have the specific heat? Well, what's our substance? It's ethanol. Do we have that? If you go back up to this table, we do have that. Which one do we want? Do we want 0.59 or 2.5?
2.5.
2.5, because we want the one with joules in it. Okay. So the confusing part to people here is I'm going to plug in all my units for specific heat. So it's going to be 2.5 times joules over gram degrees Celsius. Specific heat has a lot of units. And I prefer you to write it on top and on bottom versus like this, 2.5 joules times. People are going to write it like that. But to me, that gets confusing. It really visually helps you see that you have calories on bottom, calories on top here. Grams on bottom, grams on top. And you're multiplying all this. So that's why I can cancel them out. That altogether is going to equal a number of joules. So now you just do the math. 132 times 10 times 2.5. And the only unit that doesn't cancel out in this whole problem is joules. So we're going to be left with joules on our answer. Anybody have the answer for us? Gabrielle Ashton, all say 3,300. There we go. That's a specific heat problem. You guys just did that. Good job. Questions on that? Okay. Let's predict some things right now. How could I change up this problem? Instead of solving for joules, I could ask you to solve for the specific heat, right? Is there one more to do? Gabrielle, yes. The answer is that there's actually 4 more to do on your dry lab. That's why I put them on there for you to practice, okay? And I will post a key for that dry lab after the due date. I will actually post an example problem. I'll pick one of the specific heat problems and work it out and post that video on Blackboard. Probably tomorrow sometime, okay? Because remember that dry lab's not due till February 7th. So you have some time, but go ahead and start trying to practice them on your own, using this as an example. But think about it. I could ask you to solve for, if you look at this equation, I could ask you to solve for any part of this. I could say solve for grams. How many grams? And then you just rearrange, get grams by itself. If I ask you to solve for specific heat, that's a cakewalk, right? Because you don't even have to rearrange the equation. You just plug everything in on the right side. So think that don't allow your brain to overcomplicate these. It's all simple algebra, moving things around. With this equation, I could just ask you to solve for different parts of it. Okay. All right, that is specific heat. Let's talk about density. And anything we don't get to today, we'll either pick it up next week, or I might post a supplemental video because really we just have a lot of problems after this. And let's see, we get done at 9:15. Okay. So density, that's another property we can measure when it comes to matter. Okay. So I have a picture here. We're going to define density, and then I'm going to ask you a question about this picture. So density is this. It's mass of a substance divided by the volume of that substance. Mass divided by volume. All right. And density, because of that, can have these units. Mass has units of grams. So we can have right over here, grams divided by milliliters. Or remember that I told you 1 milliliter is also equal to 1 cubic centimeter. So it could also be grams per cubic centimeter. All right. Because 1 milliliter equals 1 cubic centimeter. Okay, so that's the equation for density. Those are units for density. Look at this picture right here. If I had to ask you, if you had to answer, which one is more dense? Which cylinder? So we got 2 cylinders, one on the right, one on the left, and the red spheres indicate some kind of matter. Maybe it's a gas, maybe it's a helium tank, I don't know. Which one is more dense? Which one has a higher density? The one on the right or the one on the left? Okay, I'm seeing in the chat the right one. Okay, so yes, this one right here is, this one is more dense. Okay, because if we took a portion of this cylinder, so some unit of volume in both of these, if I just took the bottom left corner and said, I'm going to measure this volume of the cylinder, we see that the one on the right has more mass in it. It's got more red spheres than the one on the left for any given unit of volume. Okay, so that's how you measure density. I'm going to give you this table right here. It just shows you densities for different kinds of matter, gases, liquids, and solids. Okay, so matter in different physical states. And what do you notice? Look at these values. Here's the densities of these different, here's the gases, here's the liquids, and this column on the right are all the solids. If you're just comparing the densities, which kind of matter tends to be less dense? Gases, liquids, or solids?
Gases.
Gases, okay, because gases can spread out. They're really not confined to a particular volume unless we force them into a container. But even then, they always fill the container that they're in. Okay, so gases are always going to be less dense. Solids are always going to usually be the highest, have highest density. Okay, you have the most amount of matter in a solid per unit volume than you do gases or liquids. Okay. A couple of things that I want you to also know is that density is temperature dependent. Density is temperature dependent. What does that mean? That means that density can change if temperature changes. Okay, it's not just necessarily a static thing. Why is that? Well, if you have an ice cube and you increase the temperature, now you have liquid water. And guess what? On this table right here, we're shown the densities for both of those things. Now, I know the difference is not large, but it is different, okay? Water is actually a higher density than ice, okay? Anybody ever put a bottle of water, a closed bottle of water, or a can of soda in the, we love like sparkling water. So there's one time I put a whole case of them in the freezer, bad idea, and you forget about them. Okay, what happens? You're in a confined volume. You have a particular amount, particular volume of water. And as water freezes, it expands. Okay, that's why the density, because the volume increases, that's why the density is lower. Okay, so density is temperature dependent. Just remember that. It can change if temperature changes. Density can be treated as a conversion factor. Okay, what 2 units? Remember, conversion factors just relate units, okay? Milliliters to liters. What 2 units is density relating? Units of mass and units of volume, okay? Grams and milliliters. So you can convert back and forth either way between milliliters and grams with density of a particular substance. We're going to do a practice problem here in a minute. Just to kind of check your comprehension. Okay, if we had a liter of feathers and a liter of bricks, I know this is a silly example, but I think it gets the point across. We have a liter of both, so the volume is no different. The volume is the same here, but which one is more dense? Obviously, Pernell says the bricks, okay? So why? Because there's more mass in those bricks. They're going to feel heavier, right? Because there's more. So as mass increases, if you have the same volume, density increases. And I'm going to put at constant volume, okay? Because we said we had a liter of both. Our volume's not changing. So at constant volume, the more mass you have in something, the more dense it is. Questions on that? All right, let's look at another quick example, then we're going to use density as a conversion factor. The question here is which one is least dense? Notice we have 1 kilogram flour, 1 kilogram rice, 1 kilogram of coins. Okay, so what is the same here? The mass is the same. You have a kilogram of all of these things, but notice they're different sizes. So the volume is changing here. So which one is going to be the least dense if you just had to guess?
Flour.
The flour, right? Why? Because it has the largest volume, okay? Same amount of matter, but the largest volume. So what the principle here is that as volume increases at constant mass, density does what? As volume increases, density decreases, because we said which one is the least dense, which one has the smallest or the lowest density. So the principle is that as at constant mass, as volume increases, density decreases. Questions on that? Okay, now we're going to do a practice problem. And I will say, again, I've been getting emails from students. I'm a little bit nervous about this class. Chemistry is not my strong suit. I wish I had a quarter for every time somebody's told me chemistry is not my strong suit. Okay, basically you can just tell me I hate chemistry. I'm just kidding. Don't tell me that. Okay, I know chemistry is not a lot of people's strong suit. Here's one tip. I'm going to give you one tip. If you want to succeed in this class, working problems with us is the key. A lot of people, because we're on videos and Zooms especially, they just watch me do it and they think, oh, I can just go watch it later. I promise you, if you will take the time to get out pen and paper and write these down and work them out with us and try to think ahead of me, you will have better chances of succeeding in this course, okay, on the exam. So please, that's my sermon for the day on practicing problems with us. So we're gonna use density as a conversion factor. It says you need 25 grams of rubbing alcohol. What volume of rubbing alcohol should you retrieve if the density of rubbing alcohol is 0.7855 grams per milliliter? So we're going to use density as a conversion factor, okay? So this relationship right here, the density that I just boxed in, I'm gonna rewrite it. What that means is 0.7855 grams of rubbing alcohol is equal to 1 milliliter of rubbing alcohol. We can only write this for rubbing alcohol, okay? So I've just rewritten the density as a relationship. We're gonna plug this in as a conversion factor. So I'm gonna start with 25 grams. That's what the problem gives us. We wanna know, okay, if all we have is rubbing alcohol in a liquid, so I'm not gonna go weigh this out. I'm just gonna get a certain volume of it. How much do I need? So we're gonna multiply by this conversion factor now. We're just gonna turn density into conversion factor. We want grams to cancel, okay? So it's just like we're converting milliliters to liters here, but we're just converting between grams to milliliters this time. So 0.7855 grams will go on bottom, and then 1 milliliter on top. I will see a lot of people do it this way as well. You'll set up kind of a ratio. Here's how a lot of people like to work it. You'll say 25, sorry, actually I'm gonna start with the density stuff. You say if 7.7855 grams is 1 milliliter, they'll say 25 grams is question mark, or you'll put an X there, okay? And then you solve for the X or the question mark. And that's totally valid. You're actually doing the same thing we're doing. You're just setting it up in a way that makes sense to you, and that's great if you like that, okay? But I'm gonna cancel out grams, convert to milliliters. So you're gonna do 25. You do have to multiply by this one right here, okay? You cannot ignore that. Why? That one is actually a placeholder for your 0.7855. It tells you need to divide by 0.7855, okay? So you're gonna do multiply by 1 over 0.7855, or just divide by 0.7855. And then what do we get? 25 times 1 over 0.7855 is what? Gabriel says 31.83 question mark. Okay, anybody get the same thing? Yes. Okay, thank you. So that's an example using density as a conversion factor. Okay, we're gonna do one more problem on this, one more practice, and then we're gonna move on to some complex conversion problems with the time we have left. Okay, so here's another one with density. It says the average density of human blood is 0.00106 kilogram per cubic centimeter. These are very odd units, okay? If the average adult also has a volume of 5 liters of blood, what is the mass of blood in the average human body? So we commonly know, oh, 5 liters. Like if you hear somebody say they lost a liter of blood, you're like, oh gosh, that's a big deal, okay? Because we know we only have so many liters of blood in the human body. So we just want to know, okay, how much does that 5 liters of blood weigh? What mass of our body is blood? And we're going to use density to convert. So we're given some very odd units though. So there's some extra steps we're going to have to do. So we are going to write, I encourage you when you have a problem like this, go ahead and write out any relationships you see. Anytime you see this little slash, there's a relationship there. Or anytime you can tell 2 units are being related, there's a relationship there. So I'm going to write these out, 0.00106 kilograms of blood equals 1 cubic centimeter, or I'm going to go ahead and write this. We know 1 centimeter equals 1 milliliter, okay? So I'm just going to rewrite this because we know 1 milliliter equals 1 cubic centimeter. So I'm just going to go ahead and write it as 1 milliliter. Why? Because we're dealing with liters of blood later in the problem. So I'm going to go ahead and kind of convert it to something a little more similar. All right, so that's the density of blood. And then it says that 1 adult has 5 liters of blood. Okay, we can relate those 2 things. All right, what is the mass of blood? So what is the mass of blood? What are units of mass, by the way? Because I actually don't tell you what units to give me on your answer. I just say, what's the mass? So you have to know what are units of mass. Anybody give me an example?
Kilogram.
Kilogram, okay? So we'll just get our answer in kilogram. You can convert it to grams if you want, because that's the base unit for mass, but you don't have to. The problem doesn't say how many grams of blood. It just says what's the mass. So if you give it to me in kilograms, that's totally fine. So because of that, I'm going to start with, we got 5 liters of blood. Okay, and I'm trying to convert this to kilograms. All right. I have a relationship for how many kilograms are in a milliliter, but we're going to have to do one more step. Anybody can think of one more step we're going to have to do because we have liters right now. We know how many liters of blood are in the human body. We don't know how many milliliters of blood are in the human body. So what's somebody I want to see if somebody can direct me here. What's one thing I should do?
5 liter is 5,000 milliliter.
Okay, 5 liters is 5,000 milliliters. So what, who said that, by the way? I can't see. I guess I'm calling you out. Thank you to whoever said that. They just converted liters to milliliters, okay? So you can go ahead and just say, oh, 5,000 milliliters if you want, or I'm gonna go ahead and work out the conversion, okay? So I'm gonna actually undo what I just did. I know that for every 1 liter, there's 1,000 milliliters, okay? So liters are gonna cancel. Now I'm in units of milliliters. So I just converted to milliliters. If you do the math there, yes, 5 times 1,000 is 5,000. Now I can convert from milliliters to kilograms. And that's what I want my answer in. That's gonna give me the mass of blood. So I'm gonna plug in the conversion factor. Remember, this is density. So this is how we're using density to convert from milliliters to here, kilograms. So for every 1 milliliter, I want milliliters to cancel. It's 0.00106 kilograms. And milliliters are going to cancel out. Now when I do all the math, 5 times 1,000 times 0.00106, we'll see how many kilograms of blood are in the human body. Anybody have that? Okay, we got 5.3. Y'all get the same thing? Okay, good deal. So any questions with how we could use density as a conversion factor? I promise there will be a density problem on your first exam. All right. This is where we're going to end for, well, this is the subject we're going to end with. We're not done. We still have a little bit of time. But this is kind of the last thing we're going to talk about today. And I won't have time. If you look, I've got like 4 problems down here. I'm not going to have time to go through every single one of these. So we might get through 1 or 2, and the other ones we don't get to. I want you to attempt them on your own, but I will post a video on how to solve 1 or 2 of them. And then I might save one for lecture on Thursday. Okay. Can you scroll back up to that density problem? Yes, I can. So, all right. Are you good with the density problem? Yep. Okay, good. Complex conversions. So this is where people kind of get scared sometimes. I will tell you, of all the stuff we've gone over so far, this will be the hardest, okay? But that's not a reason to be scared, because we've been building the tools and the skills for how to do these all along the way, all right? So what is a complex conversion? It's just a conversion that requires multiple steps. Okay, we actually just did one. Okay, this required like 3 steps, all right? So, and we're converting between multiple types of units, all right? Or unusual conversion factors. So that is why we call them complex conversions. You usually have many different units you're working with, and it's usually 2, 3, 4, 5, 6 steps sometimes, okay? So here's some tips as we go about these. The way you've been seeing me work them may not be your favorite way. I'm never going to say you have to work things exactly the way I do, but I'm just going to show you how I do it. And the way I like to do it is this style right here. Okay, I like to line everything up in one giant problem. Why do I do that? Well, for me, it helps me see how units cancel out. Okay, it helps me easily follow that. That's why I do it this way. And then for me, it lines the math up really easy. Okay, so I'm just going to do the math across the problem and plug it into my calculator that way. So those are some reasons I do it like this. And that's what I mean when I say do all the conversions in one problem. This is what it looks like to me, doing it all in one problem. Sometimes people on your exams, like back in the dinosaur days when we used to have paper exams, they would start their problem. Step 1 would be here, and then step 2 would be over here, and then step 3 would be up here. I literally have to do like a scavenger hunt sometimes to grade people's papers. And I get it. You're just trying to work it out the best you can, but it usually helps if you can keep it all in one continuous flow. All right. Also, another tip, write down all the conversion factors. Okay, so that's what we started to do up here, is we were just writing down different relationships, and then we just plug them in so that the units cancel. That will typically is a tip that I find helps students. And then where do you start? This is sometimes students' biggest question. How do I start the problem? Well, usually you can start, not always, but usually you can start with the first number or conversion factor that's given to you. I will tell you a foolproof way is you need to ask yourself, what kind of unit do I want in my answer? Okay, so for example, if we go back up to this density problem, the question said what mass? And we had to do some figuring here, but we said, oh, units of kilogram, that's mass. So I wanted kilogram in my answer. You could always start by plugging in the unit or the conversion factor that has kilogram in it. Plug that in with kilogram on top. Use it first. And that's a foolproof way to know that you will get kilograms in your final answer and it will be on top. Okay. Sometimes people do all this work and do all these problems and they end up getting some number and they get 1 over kilogram. And that's actually not correct. Okay. It matters that kilogram is on top here. Okay. And then again, this is what I just hit, but you want the desired unit on top. And sometimes you want it on, you have like kilogram per human adult or kilogram per body. Okay. If we wanted to write it out that way. Okay. Here's a fun one that I always like to start with, because it's always very relatable. Anybody been pulled over before? There's no judgment here. It's a judgment-free zone. I got pulled over like 3 times my first year of college, because I couldn't figure out how to slow down. So I did get tickets. I'm not like some of you. I can't talk my way out of things. You get pulled over by a cop and they're going to give you a ticket for going 0.028 kilometers per second. And you are in a 55-mile-per-hour speed zone. Where are you speeding? Okay. And if you were, can you talk yourself out of this one, you think? So we're given this relationship 1.61 kilometers per mile. Okay. So here's the deal. We're given lots of numbers and lots of units in this problem. And I will tell you, you always need to check for this. One of these numbers, we're not actually going to plug into the problem. Okay. If you are ever given a standard or a ratio that you're just supposed to compare it to in the end, like here, we are taking our speed and we're comparing it to the speed limit, 55 miles per hour. So we're actually not going to plug in 55 miles per hour in the problem. We need to take our speed and convert it to those units, okay? Miles and hours. Right now we have kilometers and seconds, okay? We need to see what is the equivalent number in miles and hours, and we're just going to make a comparison, okay? So always check your problem. Do I have just a ratio or a standard here that I'm just supposed to compare to in the end that I don't actually use in my problem? All right, so start with 0.028 kilometer per 1 second. That's what that relationship is. That was your speed. And the reason I wrote it like this is because we want units of distance on top. Kilometer is a distance, it's a length. And we want time on bottom. Seconds is time, so we're putting that on bottom. And then we need to convert. So we're actually given 1.61 kilometer per mile already. So we don't have to write this out because it's given to us. So I'm just going to plug it in because we know we need to convert kilometers to miles. So you want kilometers to cancel. So you do the 1.61 on bottom for every 1 mile. Now kilometers cancel. Notice, I think this is an added layer of difficulty because we have a unit on bottom now that we have to account for as well. We need to convert seconds to hours. So I'm just going to continue my problem. Don't get confused by what I'm going to do. I'm just going to write another conversion factor. I've got seconds on bottom down here. How do I convert to hours? Well, how would you do it? You add 60 seconds on top and 1 hour on the bottom. Okay, we got one step we're missing. There's 60 seconds in a minute,
60
or
minutes in an hour.
okay, yeah, you could do it 2 ways. You could do seconds to minutes, then minutes to hours, or I'm seeing in the chat people looked up how many seconds are directly in an hour. That's fine too. You can do 3,600 seconds are in 1 hour. And this is just one less step. But the seconds to minutes, minutes to hours is fine too. All right, now seconds cancel because I've got it on bottom and on top. So look, the only units that don't cancel are miles and then the per hour, whatever is per is on bottom. So miles per hour, which is what we want because that's exactly the way the speed zone is written. So now we're just going to do this math. 0.028 divided by 1.61 times 3,600. If it's on bottom like this, you divide by it. If it's on top like the seconds, you multiply by it. Okay, we got an answer of 62.6. The units here are miles per hour. Okay. Yep, you are speeding. But who thinks they could talk themselves out of that one? Like, no big deal. Come on, officer, I wasn't going 20 miles over. I was just going like 10, basically 5 if you round down. Okay. All right, so that's a complex conversion problem, right? How do y'all feel about that? Are you sweating? Are you still alive? Okay, good. So guess what? We got 1, 2, 3 problems. I'm going to save one of these for Thursday. I think I've beaten your brains enough today. I'm going to do a video on 1 or 2 of them, but here's what I don't want you to do. Don't just watch that video. Try to do the problem yourself first. And then if you just absolutely get stuck, use the video as a guide, okay? But please, please, you'll help yourself the most if you try it on your own first. So scrolling down, you guys help me fill in this slide. What did we learn today? What's just a summary? What were the big takeaways from today? Density, we learned about density,
Heat.
specific heat,
Energy.
which is involved energy. Okay. And energy, units of energy. Oops, that's not how you spell units. Complex conversions. One more thing, we're forgetting one. Oh, I see it. No, we're not. Temperature. Okay, 1, 2, 3. These were the 4 big hitters today. So we got about 5 minutes left. And honestly, if anybody wants to stick around, I'm going to go ahead. Sure, I'll work another problem in 5 minutes. But officially, I'm saying lecture's over. If you got to go, if you want to go, if you're tired of looking at this screen, then this will all be on the video recording if you want to catch it later. But if you want to work another problem, there was a question, can we do one more? So I'm never going to, that's like my child asking me, can I have more broccoli? I'm never going to say no to that. Okay. So let's look at one more. You have a vial of a drug solution and it's 65 milligram per milliliter. Your patient needs 7 milligrams of the drug for every kilogram of body mass. The patient weighs 150 pounds. How many milliliters of the drug should you administer? Okay, so we got lots of different units here. Again, if you got to go, thanks for joining us. How do we begin to handle this? So first off, what is the question asking for? Here's the question right here. How many milliliters of the drug should you administer? So you want, in your final answer, you want units of milliliters. All right. Now we've got several relationships, and I'm just going to start writing those relationships on the left side of my screen. The first relationship I notice is given to me right here. Anytime you see 2 units put together, that's a relationship. So it tells us that our vial of our drug solution is 65.0 milligrams for every 1 milliliter of solution. There's 65 milligrams of the drug for every 1 milliliter of the solution that the drug is in. Says your patient needs 7 milligrams of the drug for every kilogram body mass. When you deal with patients, you always have to take into account how much that patient weighs. So that's another relationship, 7 milligrams of the drug for every 1 kilogram of body mass. Now notice right here, when you start to deal with lots of different units and stuff, I sometimes put in these little descriptive words that help me remember what we're talking about. So that's why I'm writing in the drug here and things like body mass, but you don't have to. It just helps guide me on the problem. All right, and then your patient weighs 150 pounds. So notice we have a number here that's not related to anything, okay? It's just a random number, but we will use it. We also have another relationship. I'm not going to rewrite this, but 2.2 pounds is 1 kilogram. So the question is, how many milliliters of drug should you administer? So I want units of milliliters in my answer. And if you remember, I said this earlier, here's the question people have, where do I start? What thing should I plug in first? I'm going to find my conversion factor that has milliliters in it, and I'm going to write it with milliliters on top. I promise you this is a foolproof way to get the correct units where you want them. And so that is this relationship right here. I'm going to come down here. For every 1 milliliter of solution, we have 65 milligrams of drug. Now I have milliliters on top. I'm going to go about canceling out every other unit except milliliters. So, and this is drug. So I also, if I have 1 milliliter per 65 milligrams of drug, my next relationship says for every 7 milligrams of drug, that's how many milligrams of drug, 1 kilogram of body mass for the patient. Okay, so for every 1 kilogram body mass, we're supposed to give that patient 7 milligrams of the drug. I want to cancel out milligrams down here. I don't want that in my answer. I just want milliliters. So I'm going to cancel milligrams by plugging in the 7 milligrams on top for every 1 kilogram of body mass. So milligrams are going to cancel. Okay. I don't want, now I have milliliters on top and kilograms on bottom. I don't want kilograms on bottom. I want to cancel that as well. So I have this conversion factor right here that lets me convert from kilograms to pounds. So I'm just going to plug that in. For every 1 kilogram, it's 2.2 pounds. Notice that I'm not even really analyzing the problem all that much. I'm just letting the units guide me, okay? And I get it. This probably feels really new and uncomfortable for a lot of you. The more you practice it, the more comfortable it will become. So kilograms cancel. Now I have milliliters that still have not canceled, and I have pounds on my last conversion factor, has not canceled. I need to cancel pounds. What can I do? I have a random number up here that I still need to use. My patient is 150 pounds, and I can use that to cancel pounds if I multiply by 150. So I have it on bottom and I have it on top, it cancels. So I just went about canceling every unit that I don't need except for milliliters. So now you'll do not ignore this initial 1 right here. There's a 1. So do 1 divided by 65 times 7, divide by 2.2 times 150. Can anybody tell us how many milliliters of that drug solution we need? Anybody got 35.5, Gabrielle says? Is that what you got? Anybody can confirm or deny? Okay, we got a different number. Okay, I'm seeing 7.34. Okay, maybe you forgot to divide by our multiple. I don't know what happened, Gabrielle. It's okay, though. Props to you for trying. 7.34 milliliters seems to be the more common answer. So that's another example of a complex conversion problem. We are over time now. I'm going to be on an office hour in about 15 minutes. If anybody wants to just hop on and ask me any questions. If you have questions now, though, I'll hang around for another minute or two. But if not, thanks for joining. There's a question about lab for this Friday. Maria, what is that? If not, thanks for joining. See y'all on Thursday. Don't forget your quiz. Are we supposed to go? Okay, the answer is it depends. It depends if you're group A or if you're group B. All right, so group A people. Okay, Addie, if you don't have a lab assignment, please send me an email. If you were recently added to the course like this week, I've checked my rosters again yesterday and I noticed a couple new emails. So email me and I'll get you a lab assignment pronto. But if you're in group A, you show up to lab this week. So like yesterday in the Monday group, we had all the group A people show up. The group B people, you can spend that time working on the dry lab. But we're not meeting on Zoom because I am in lab with the group A people. So I'm not able to host a Zoom session. So this week you kind of just spend that time working on the lab on your own. And the next week the groups will switch. Group A people will be on their own working on the dry lab. Group B people will come into lab. And then the following week after that, we'll start our Zoom breakouts and we'll do labs together on Zoom. Let me catch up on the chat. Can you write down in words how you start so I remember later? On this slide is fine. Are you talking about how I